What if I told you there's a forgotten, satisfying muscle car so aerodynamically dominant that an entire racing sanctioning body had to completely rewrite their rulebook just to neutralize it? Not because it was cheating, not because it was unsafe, but because it was simply too good, too fast, too perfect at doing the one thing nobody else had figured out yet, turning thin air into an unfair advantage. Picture this for a second. It is February 1969. The green flag drops at Daytona International Speedway. David Pearson's midnight blue Ford Torino Talladega rockets off the banking and into the lead. By the time he crosses the finish line, he has averaged over 157 miles per hour for 500 grueling miles. The competition is not just beaten, they are psychologically broken. Demoralized. Standing in the garages afterward, crew chiefs from rival teams are not angry, they are confused. They cannot figure out how a car that looks almost identical to a standard Ford Torino is suddenly untouchable on the biggest tracks in America. This is the story of the Ford Torino Talladega, the car that weaponized aerodynamics before anyone else even understood what the word meant in stock car racing. The car that scared NASCAR so badly they essentially banned an entire class of vehicles from competition, and the car that still, more than 50 years later, influences every single race car that rolls onto a track anywhere in the world. This is legacy motoring, and I spend way too much time thinking about the intersection of engineering brilliance and racing history. If you are someone who loves understanding why certain cars changed the game forever, and how a manufacturer's obsession with winning reshaped an entire sport, make sure to hit the subscribe button and give this video a thumbs up if this helps you out. Now, to understand why the Talladega even exists, you have to understand what was happening in NASCAR in the late 1960s. Here's the thing. For years, stock car racing had been a horsepower war. Whoever could cram the most cubic inches under a hood and make the most power on a dynamometer usually won. It was simple, brutal, and effective. But something was changing. NASCAR superspeedways had exposed a truth that most teams were completely ignoring. At speeds approaching 200 miles per hour, aerodynamics mattered more than cubic inches. Way more. You could have 800 horsepower under the hood, but if your car had the aerodynamic profile of a refrigerator, you were losing to the guy with 600 horsepower and a slippery body. Dodge had actually fired the first real shot in the Aero wars. They took their standard Charger, which had this beautiful but terribly aerodynamic recessed grille and tunneled rear window, and they smoothed it all out. They called it the Charger 500. The recessed grille got filled in flush. The rear window was replaced with a piece that sat even with the C-pillars. And suddenly, this thing could slice through the air like nothing else on the NASCAR circuit. Ford's boxy Torinos, which had been competitive, were suddenly getting embarrassed on the high banks of Daytona. And then Bill France went and opened Alabama International Motor Speedway, which would later become Talladega Superspeedway. 33-degree banking, 2.66 miles around. This was not just another racetrack. This was the fastest closed course on the planet Earth, a place where aerodynamic drag would be the single biggest factor separating winners from also-rans. And Ford knew it. They knew that if they showed up to this track with the standard Torino, they would get absolutely destroyed. Ford's racing director, Jock Pacino, understood the assignment. He knew they needed something radical, something that went beyond bolting on a bigger carburetor or advancing the timing a few degrees. The standard Torino's flat nose was creating a wall of air resistance at high speed. Wind tunnel testing at Ford's Dearborn facility showed it had a drag coefficient of around 0.42. To put that in perspective, that is about as aerodynamic as a cinder block. Every mile per hour above 150 was a battle against physics, and the Torino was losing that battle badly. So Pacino made the call. He reached out to Ralph Moody at Holman Moody, the legendary racing preparation shop in Charlotte, North Carolina. Ford needed a Torino that could cheat the wind, a car that could do at 190 miles per hour what a standard Torino could only dream of. And they needed it fast. The 1969 Daytona 500 was months away. The clock was ticking. But here is where it gets really interesting. NASCAR had this rule called the homologation requirement. Any car you wanted to race had to have at least 500 street-legal versions produced and available for sale to the general public. You could not just build a couple of wind tunnel specials, slap a Ford badge on them, and show up at the track. You had to commit. You had to put your money where your aerodynamic data was. Ford had to build real cars, sell them to real people, and prove they were legitimate production automobiles. That requirement changed everything about how Ford approached the project. This was not going to be some secret skunkworks prototype. This was going to be a production car. The transformation began inside Ford's wind tunnel in Dearborn, Michigan. Engineers spent hundreds of hours testing scale models and full-size clay mock-ups, methodically reshaping every surface of the Torino's front end. And what they discovered was almost elegantly simple. Extending the Torino's nose by just 6 inches would dramatically reduce frontal air pressure. They were not adding horsepower, they were removing resistance. Think about it like this. Imagine you're running through waist-deep water. You could spend all your energy pumping your legs harder, or you could find the path where the water is only ankle-deep. Ford chose the shallower water. The grille was laid back at an angle, sitting flush with the hood line instead of standing upright like a wall. The front bumper was rolled under and tucked tight against the body, eliminating the shelf of dead air that normally formed underneath a standard chrome bumper. The rocker panels were re-rolled to sit approximately 3 inches lower than stock, smoothing the airflow along the sides of the car where turbulence loved to gather and create drag. But the real genius was in the details nobody could see from 20 feet away. The entire front clip was redesigned with gently rounded edges instead of the sharp corners found on a production Torino. Even the headlight bezels were reshaped to eliminate tiny pockets of turbulence that would seem insignificant on paper but added up to measurable drag at race speeds. Ford's engineers were thinking in millimeters, obsessing over every single surface transition, knowing that at 190 miles per hour, a quarter-inch ridge or a poorly fitted panel gap could cost you 2 miles per hour on a straightaway. 2 miles per hour does not sound like much until you realize that over the course of a 500-mile race, that tiny aerodynamic penalty translates into being hundreds of yards behind the leader at the checkered flag. Here's what most people do not realize about how the production Talladegas were actually built. Each one started life as a standard Torino on the assembly line at Ford's Atlanta plant. Workers would install the unique extended front clip, the modified grille, the reshaped bumper, but then something unusual happened. Instead of rolling off the line complete and heading to a dealer lot, these cars were shipped to Holman Moody's facility in Charlotte for finishing. This was not just your typical dealer prep where some kid washes the car and puts floor mats in it. This was race-level attention to detail on a production automobile. Holman Moody's technicians would go over every single car by hand. They hand-fitted every panel gap, ensuring perfect alignment between the fenders, hood, and nose extension. They massaged the sheet metal in areas where the stamping dies had left tiny imperfections or wrinkles. They even checked and adjusted the angle of the rear window to optimize airflow separation at the trailing edge of the roof. These were production cars being given the kind of attention normally reserved for actual race cars. The result was a level of fit and finish that no other Ford product could match. Under that sloped hood sat Ford's formidable 428 Cobra jet engine. Officially, Ford rated it at 335 horsepower. But look, everyone in the industry knew that number was deliberately conservative. Manufacturers in the late 60s routinely underrated their engines to keep insurance companies and regulators happy. With its 10.6-to-1 compression ratio, solid lifter camshaft, and 735 CFM Holley 4-barrel carburetor, the real output was much closer to 400 horsepower. The engine breathed through a ram air induction system that ducted cool, dense outside air directly to the carburetor. Cold air is denser than hot air, which means more oxygen molecules per cubic foot, which means more power. Simple thermodynamics delivering real-world results. The drivetrain was built to handle sustained high-speed punishment. The C6 automatic transmission was beefed up with a 2,800 RPM stall converter and heavy-duty clutch packs designed to survive repeated wide-open throttle runs. The 9-inch rear end, one of the strongest axle assemblies ever put in a production car, packed 3.25-to-1 gears with a traction lock limited slip differential. This gearing was specifically chosen for superspeedway use, tall enough to allow high top speeds, but with enough multiplication to get the car up to speed efficiently. Ford built exactly 750 street Talladegas between January and March of 1969. They came in just 3 colors: Wimbledon white, royal maroon, and presidential blue. No racing stripes, no hood scoops, no wings or spoilers. The only external clues that you were looking at something special were the extended nose, the flush-mounted grille, and small Talladega badges on the rear quarters. Most buyers walking past one on a dealer lot would have assumed it was just another Torino with a slightly different front end. They had no idea they were looking at a homologation special, a car built specifically to satisfy NASCAR's production requirements so that its race-bred aerodynamics could compete on Sundays. The sticker price was $3,680, which translates to roughly $29,000 in today's money. For comparison, a base Torino GT cost $2,940, so you were paying a premium of about $740, roughly $6,000 today, for the aerodynamic modifications and Holman Moody finishing. Whether buyers understood what they were getting for that premium is debatable. Most probably just liked how the car looked. Now, you might be thinking, okay, so it was a slightly slipperier Torino with a hot engine. What is the big deal? The big deal is what happened when the racing versions hit the track. The race cars were a completely different animal from the street versions. The 428 was yanked out and replaced with either the 429 Boss or the legendary 427 FE, both pushing well over 500 horsepower in full NASCAR trim. The suspensions were completely rebuilt from scratch, with fabricated tubular control arms, coilover shock absorbers, and massive anti-roll bars. The bodies were acid-dipped, a process where the entire body shell was submerged in an acid bath that dissolved a thin layer of steel from every panel, removing every possible ounce of unnecessary weight. Then, the lightened bodies were strengthened with full roll cages that tied into the frame rails at multiple points, creating a rigid safety structure. And the wind tunnel numbers for the finished race cars were absolutely staggering. The production Talladega achieved a drag coefficient of 0.30, which was already better than a contemporary Corvette. The race cars, with their perfectly smooth undersides, taped panel seams, and meticulously aligned body panels, got the number down to 0.28. Now let me give you some context for how remarkable that is. A modern Toyota Camry, designed with decades of computational fluid dynamics and computer modeling, has a drag coefficient of about 0.27. A 1969 stock car was achieving virtually identical aerodynamic efficiency to a 2024 family sedan. That fact alone should tell you everything about how far ahead of its time this car was. Dodge was not sitting still while Ford was rewriting the aerodynamic playbook. They responded to the Talladega with a Charger Daytona. And if the Talladega was a scalpel, the Daytona was a broadsword. That famous pointed nose cone extending nearly 2 feet beyond the standard Charger's front end. That towering rear wing standing almost 2 feet above the trunk lid. The Daytona looked like nothing else on the road or the track, and it was genuinely fast in a straight line. But here's the thing about the Daytona that most people do not talk about. It was also unstable in traffic and at certain speed ranges. The massive rear wing generated enormous downforce on the back of the car, which sounds great until you realize that all that downward pressure on the rear axle was simultaneously reducing the load on the front tires. At certain speeds, typically around 185 miles per hour, the interaction between front lift and rear downforce created a condition drivers described as spooky. The car would feel light and unpredictable at the front end, like the steering was connected to nothing. The Talladega, with its more balanced and integrated aerodynamic design, did not suffer from this problem. It was predictable and confidence-inspiring right up to the limit. Drivers trusted it, and in racing, trust translates directly into speed, because a driver who trusts the car will push harder into corners and hold the throttle open longer on the straights. The first major test of the Talladega came at the 1969 Daytona 500. Leroy Yarbrough put his Talladega on the pole with a qualifying speed of 194.015 miles per hour. During the race itself, the drafting battles were unlike anything NASCAR had ever witnessed. Cars were running in tight packs at speeds that had never been seen before in stock car racing. Yarbrough went on to win the race, but the real story was not the finish, it was the pace. The race average of 157.95 miles per hour shattered the previous record by nearly 7 miles per hour. That is an enormous jump in average speed for a 500-mile race. It signaled that something fundamental had changed in NASCAR competition. Then came Talladega Superspeedway in May of 1969, and this is where it gets really interesting. During practice sessions, drivers were routinely touching 200 miles per hour down the backstretch. 200 miles per hour in a stock car in 1969. Think about the tires those cars were running on. Think about the safety equipment available at the time. Open-face helmets, lap belts, no Hans devices, no energy-absorbing barriers, just concrete walls and steel guardrails and a prayer. And the tires were not designed for these speeds, not even close. Firestone and Goodyear were witnessing catastrophic failures during practice, tread separation at full speed. The tires would simply come apart, the tread peeling off the carcass like a banana skin, sending 3,400 pounds of steel sliding sideways at nearly 200 miles per hour. Several drivers crashed during practice when their tires exploded without warning. There was no gradual loss of grip, no gentle vibration to warn you. 1 second you were at full speed, the next second you were a passenger in an uncontrollable projectile. The situation became so dangerous that the majority of top drivers, including Richard Petty, the king himself, organized a boycott of the inaugural Talladega race. Bill France was absolutely furious. He had just built the biggest, fastest track in the world, and his star drivers were refusing to race on it. But the drivers had a legitimate and terrifying point. The combination of the new aerodynamic cars and Talladega's extreme banking had pushed beyond the absolute limits of tire technology. They were being asked to risk their lives on equipment that was demonstrably inadequate for the speeds involved. The race went ahead anyway, with a depleted field filled with replacement drivers and independent teams desperate for the exposure. Richard Brickhouse won in a Dodge Daytona, earning the only victory of his Cup career. But the writing was on the wall in letters 10 feet tall. The Aero cars had pushed NASCAR to its breaking point. By the end of the 1969 season, the Talladega had accumulated 26 race victories. David Pearson, one of the greatest drivers in NASCAR history, captured 11 of those wins on his way to the Grand National Championship. Donnie Allison, Cale Yarborough, and Dick Brooks added more victories throughout the season. Ford's domination of the superspeedways was so complete, so utterly one-sided, that Chrysler, the parent company of Dodge and Plymouth, actually threatened to withdraw from NASCAR entirely unless the sanctioning body did something to level the playing field. Now, let me explain why the Talladega's aerodynamic advantage was so profound from a pure engineering perspective, because this is where you really start to appreciate the brilliance of what Ford accomplished. The boundary layer control on this car was revolutionary for its era. When air flows over any surface, it creates a thin layer of turbulent, slow-moving air that clings to that surface. Aerodynamicists call this the boundary layer. On most cars, this boundary layer separates from the body somewhere around the rear window or trunk, creating a large turbulent wake behind the vehicle. This wake is essentially a low-pressure zone that sucks the car backward, like an invisible parachute dragging on the rear bumper. The Talladega's smooth, extended surfaces kept the boundary layer attached to the body for much longer than on a standard Torino. By the time the air finally separated, the wake was significantly smaller. Less wake means less drag. Less drag means higher speed for the same horsepower. The front extension was not just about moving the nose forward 6 inches. It was about managing air pressure in a fundamentally different way. At high speeds, air compresses against the front of a vehicle, creating a high-pressure zone that pushes directly against forward motion. By extending and gently sloping the nose, Ford's engineers gave that compressed air more time and more surface area to flow smoothly around the car rather than pile up against it like water against a dam. The pressure differential between the high-pressure zone at the front and the low-pressure wake at the rear decreased measurably, and that decrease translated directly into reduced overall drag. The flush-mounted grille served double duty. It reduced the car's effective frontal area while still allowing sufficient cooling air to reach the radiator. The angle of the grille was precisely calculated at roughly 35 degrees from vertical. Too steep, and it would generate front-end lift that would make the car unstable at speed. too shallow, and it would not flow enough air to keep the engine cool during a 500-mile race in the Florida or Alabama heat. At 35 degrees, it hit the aerodynamic sweet spot. Cooling drag, which is the resistance created by forcing air through a radiator and around an engine bay, was reduced by 18% compared to the standard Torino. Even the door handles received attention. Stock Torinos had slightly protruding handles that created tiny but measurable vortices at speed. The Talladega's handles were recessed just a quarter-inch deeper into the door skin. Wind tunnel testing showed this modification alone saved 0.3 miles per hour at 190. That might sound completely insignificant, but look, in a 500-mile superspeedway race where cars run in tight packs and drafts are won and lost by inches, those tiny aerodynamic gains compounded over hundreds of laps until they became the difference between kissing the trophy and watching someone else kiss it. The suspension geometry was specifically modified to achieve the ideal ride height and rake angle for high-speed aerodynamic performance. The car sat slightly lower in front than in the rear, creating a subtle wedge shape that encouraged air to flow over the top of the car rather than getting trapped underneath. Too much air flowing under a car at speed creates lift, which reduces tire contact patch and destroys stability. The Talladega's combination of lower front ride height and a relatively flat under tray minimized this effect, keeping the car planted even at its highest speeds. Here's something most people absolutely do not know. Ford actually experimented with active aerodynamics on several test mules during the Talladega's development. They prototyped a system where the rear spoiler would automatically adjust its angle based on vehicle speed. At lower speeds in the corners, the spoiler would angle upward to generate more downforce for grip. On the long straights, it would lie flat to reduce drag and maximize top speed. The system worked beautifully in testing, but it was deemed too mechanically complex for reliable race use and was clearly illegal under NASCAR's rules at the time. This concept, active aerodynamics, would not appear in production sports cars for another 20 years. Ford was 2 decades ahead of the curve. The Talladega program also inadvertently advanced tire technology in ways that benefited every driver on every road in America. The extreme speeds exposed fundamental weaknesses in tire construction that normal testing, even aggressive normal testing, had never revealed. Goodyear and Firestone were forced to develop entirely new compounds and construction techniques specifically for these aerodynamic cars. Inner liners were reinforced with additional layers of nylon cord. Bead construction was strengthened to prevent the tire from separating from the rim under extreme centrifugal loads. Tread compounds were completely reformulated for higher heat resistance. These improvements, born from the desperation of keeping race tires alive at 200 miles per hour, trickled down into passenger car tires within just a few years, making every family sedan and station wagon in America safer. Ford's engineers stumbled onto something genuinely unexpected during extended development testing. The car's aerodynamics actually improved slightly with age and use. As the paint surface accumulated microscopic stone chips and the panel gaps loosened just barely with thermal cycling and vibration, the microscopic surface roughness actually helped the boundary layer stay attached to the body for a few extra inches before separating. A well-used Talladega with a few thousand miles on it could be 1 to 2 miles per hour faster than a freshly painted, perfectly smooth example, assuming all other mechanical variables were equal. This phenomenon, which aerodynamicists call turbulent boundary layer tripping, was well known in aerospace but had never been observed or exploited in automotive applications before. The total development cost of the Talladega program went far beyond the $2 million figure Ford publicly acknowledged, which is roughly $16 million in today's dollars. Ford constructed 17 different prototype configurations, each requiring extensive wind tunnel time at approximately $1,000 per hour in 1968 money, which is about $8,000 per hour today. They crash-tested 6 prototypes at high speed, specifically to understand aerodynamic stability limits and failure modes. What happens when a car at 180 miles per hour suddenly rotates sideways? How much lift does it generate? At what angle does it become airborne? These were life and death questions that could only be answered by deliberately destroying very expensive prototypes. The computer modeling work, performed on room-sized IBM mainframes that had less computing power than a modern smartphone, cost $300,000 in computing time alone. The homologation cars presented their own unique set of engineering challenges. Ford had to ensure the street versions were close enough to the race specifications to pass NASCAR's inspection, while still being practical enough for someone to drive to work every day. And honestly, they were not entirely successful on the practicality front. The extended nose made parking in tight spaces genuinely difficult. Drivers could not see the front corners of the car, leading to countless scraped bumpers in shopping center parking lots. The low-mounted front spoiler scraped on every driveway entrance and speed bump in America. The flush-mounted grille, so brilliantly effective at race speeds, restricted airflow at low speeds, causing some cars to overheat in heavy traffic on hot days. But Ford could not change any of these features without losing the aerodynamic advantages that were the entire reason the car existed. Now, you might be thinking about the competition's response, and this is where the story gets even more fascinating. Dodge's Charger Daytona, despite looking far more dramatic than the Talladega, was actually less scientifically developed. The enormous rear wing was essentially an afterthought. Initial wind tunnel testing had shown that the nose cone alone was not generating enough overall downforce for stability. The wing was added late in development, and while it generated massive rear downforce, it also created significant additional drag. At certain speed ranges, the downforce was so severe that it would actually compress the rear suspension springs, changing the car's rake angle dynamically and inadvertently increasing front-end lift. Drivers reported the car feeling genuinely scary at around 185 miles per hour when these aerodynamic forces reached their worst interaction point. Plymouth's Superbird, despite looking virtually identical to the Daytona, was actually quite different aerodynamically. The nose cone was 3 inches longer, the rear window caps, those distinctive pieces that covered the tunneled rear glass, were completely redesigned for better airflow attachment. And the wing mounting was significantly reinforced after several Daytonas experienced wings tearing partially loose at speed during the 1969 season. A wing failure at 190 miles per hour is about as close to a death sentence as racing can deliver. NASCAR required Plymouth to build 1,920 Superbirds for homologation, more than double the Talladega's requirement, because Plymouth had a larger dealer network. Mercury also joined the battle with the Cyclone Spoiler 2, which was essentially a Mercury-badged Talladega built on the Cyclone platform instead of the Torino. Only 351 were produced, making them even rarer than the Talladega today. Dan Gurney won races in both Ford and Mercury versions of the Aero car, conclusively proving that the aerodynamic package worked regardless of which division's badge was on the trunk. The safety concerns that emerged from the Aero wars were real, immediate, and mounting with every race weekend. Bobby Allison's Talladega went airborne during practice at Talladega Superspeedway in May of 1969, launching 30 feet through the air before miraculously landing on its wheels. He walked away physically unharmed, but the incident absolutely terrified NASCAR officials. The cars were generating actual aerodynamic lift at certain yaw angles. When a car got sideways at speed, the airflow over the roof and under the floor would interact in a way that literally tried to turn the car into an airplane. This specific problem led directly to the development of roof flaps, those small panels on the roof of modern stock cars that deploy automatically when the car rotates backward, disrupting the lift-generating airflow. Roof flaps and hood pins, both born from the Aero wars, are still mandatory safety equipment in NASCAR today. The tire war between Goodyear and Firestone reached genuinely dangerous levels during the Aero wars era. Each manufacturer was pushing their rubber compounds to the absolute ragged edge of material science, and sometimes well beyond. Tires were failing catastrophically after just 30 or 40 laps at superspeedway speeds. Teams were changing tires so frequently that fuel strategy, normally a critical tactical element, became completely secondary to tire survival. The infamous Talladega boycott in September of 1969 was primarily and fundamentally about tire safety, with drivers collectively refusing to risk their lives on rubber they considered completely inadequate for the speeds the Aero cars could generate. For 1970, NASCAR introduced restrictor plates at superspeedways in an attempt to limit speeds, but it was not enough. The Aero wars continued with Plymouth Superbird now joining the battlefield. Bobby Isaacs set a closed course speed record of 201.14 miles per hour at Talladega in a Dodge Daytona. Stock cars were literally outrunning NASCAR's ability to regulate and control them. Then the hammer fell. For the 1971 season, NASCAR announced that any car featuring aerodynamic modifications, including the Talladega's extended nose, would be restricted to just 305 cubic inches of engine displacement. Standard-bodied cars could run engines up to 430 cubic inches. This displacement penalty made the Aero cars instantly and hopelessly uncompetitive. You simply could not overcome a 125 cubic inch displacement disadvantage with aerodynamic efficiency alone. Just like that, the most technologically advanced stock cars ever built were rendered obsolete by a single rule change. The end of the Aero wars was not solely about safety, though that was the primary justification. It was also fundamentally about cost and competitive equity. The factory teams were spending millions on aerodynamic research and development. Chrysler publicly claimed they lost money on every single Superbird sold to the public, even at a sticker price of $4,300. Ford's total racing budget for 1969 exceeded $7 million, an astronomical sum for the era. Smaller independent teams simply could not compete with factory-level aerodynamic development programs. NASCAR wanted to level the competitive playing field and reduce the financial barriers to entry, making the sport more competitive, more exciting, and more economically sustainable for everyone involved. But here's the thing about knowledge. Once you learn something, you cannot unlearn it. Within a decade of the Aero wars ending, every serious NASCAR team had an aerodynamicist on staff. Wind tunnels became standard development tools rather than exotic technologies reserved for factory programs. Computer modeling replaced guesswork and intuition. The Talladega had conclusively demonstrated that races could be won in the wind tunnel just as surely as they could be won on the racetrack. That philosophy drives NASCAR's development to this day, with teams spending millions annually on aerodynamic optimization within the sport's increasingly strict technical regulations. The collector market for Talladegas has absolutely exploded in recent years. Clean, well-documented examples now routinely sell for between $150,000 and $200,000. Verified racing history adds enormous premiums. A Talladega that David Pearson actually drove in competition sold at auction for $445,000 in 2021. Even rough project cars needing comprehensive frame-off restorations regularly bring $50,000 or more. The combination of extreme rarity, fewer than 400 street versions are believed to survive today, genuine racing provenance, and historical significance makes them blue-chip investments in the muscle car collecting world. The philosophical question that the Talladega ultimately raises is still genuinely relevant today, not just in racing, but in technology broadly. How much innovation is too much? NASCAR decided the Aero wars had pushed beyond acceptable limits. But was that the right call? Would unrestricted aerodynamic development have led to even greater technological innovations that would have benefited both racing and road cars? Or would the escalating speeds inevitably have resulted in tragedy on a scale that would have threatened the survival of the sport itself? We will never know the answer. But the Talladega stands as powerful evidence that sometimes progress has to be deliberately reined in for its own good and for the safety of the people involved. Today's NASCAR Cup Series cars, with their computer-designed bodies, wind tunnel-validated shapes, and precisely controlled aerodynamic specifications, are direct philosophical descendants of what the Torino Talladega started in 1969. The restrictor plates used at Daytona and Talladega from 1988 until 2019, and the tapered spacers that replaced them, exist specifically because of the speeds that the Aero Warriors first achieved 55 years ago. Every modern safety innovation, from roof flaps to safer barriers to the hands device, can trace its fundamental necessity back to the velocities these cars reached and the dangers those velocities created. The Talladega proves something profound about engineering and competition. Sometimes the biggest competitive advantage comes not from doing one thing better than everyone else, but from thinking about the entire problem differently. Ford did not build a more powerful engine. They built a more slippery car. They did not try to overcome air resistance with brute force. They systematically eliminated that resistance surface by surface, gap by gap, millimeter by millimeter. They did not fight physics. They recruited physics as their most valuable team member. And in doing so, they created a machine so devastatingly effective that it had to be legislated out of existence, a car so far ahead of its time that the rules of the sport literally had to be rewritten to contain what it had unleashed. The Ford Torino Talladega remains, more than half a century later, the car that was simply too good for its own good. It dominated so completely that the competitive framework had to change around it. It went so fast that the supporting technology of tires and safety equipment could not keep up. It won so frequently and so decisively that winning almost became predictable. In the end, the Talladega's greatest achievement was not the 26 races it won or the championship it delivered. Its greatest achievement was forcing an entire sport, an entire industry to evolve. And that is the ultimate legacy for any machine, to be so revolutionary, so far ahead of the accepted boundaries that the entire world has to accommodate what you have proven is possible. What do you think would have happened if NASCAR had let the Aero wars continue completely unrestricted? Would we have seen 300-mile-per-hour stock cars by the mid-70s? Would the innovation have saved lives through better technology, or would the speeds have led to disasters that ended careers and changed families forever? Drop your thoughts in the comments below. I genuinely want to hear what you think. And if you made it this far, do not forget to subscribe and hit that bell for more stories about the machines that changed everything.